Talk today is about the Renaissance project with IBM Research I'm involved in, and precisely I'm talking about the Sly language. That's a little small talk dialect and the raw VM. But before I'm going into that, I'm wearing today that t-shirt for a reason, just to point out we had a nice little Google Summer of Code project with a student called Lars Wassermann. And he implemented actually the basic foundation for an ARM just-in-time compiler for the Coq virtual machine. And if you're interested in that kind of stuff, the basic foundation is there, the simulator is working, he has a bridge to the ARM emulator, the disassembling is working, the basic jitting is also already like the foundation is all laid out. There's still stuff to do, so if you need performance on an ARM device like an Android phone or Raspberry Pi or so, you want to look into that. I think the showcase page has a nice little overview set of slides and the URLs you want to look at. So that guy did good work, and yeah, if you're interested to get performance, there's still work to do, but yeah, so the foundation is there. Okay, getting to my own talk. So what I'm going to look at briefly is what the raw VM and the parallel Smalltalk running on it is actually about, how it works, and the Sly language, which is a little research language to do parallel programming in a way that you can embrace the non-determinism of the parallel programming. And then briefly, if I have time at the end, I will look into the raw VM implementation decisions, the implementation details. First, well, I actually did only a small part in the whole thing. Most of the work has been done at IBM Research. I came later to the project. The implementation of the raw VM was done by David Unger, who also was on the Self project back in the day. Sam Adams, they invented the idea of Lie and Sly, two very related languages. And Portland State University is involved. Max Orhai was a student there. I will use one of his demos. And he had also a smart student who did a bit of performance improvement of the whole implementation. Okay, let me briefly go into what the parallel Smalltalk is about. The first thing, something, yeah, does it work? Oh, I don't see it on my own screen. One thing Stéphane Ducasse always likes to do is to teach people how to build a virtual machine. So, because it's apparently very hard. If you ever try to build your own Coq virtual machine or the Stack VM, well, you have to read long blog posts, follow step-by-step instructions. For us, it's a bit easier. So you can just basically download the code from GitHub, do a configure. If you don't know what to do exactly, there's a little help, but we don't want to do anything special. So we just do configure and then make. That might be a bit archaic, not very user-friendly, user interface-driven, but it works. And then, at the end of the day, it takes a bit. You will have your own little virtual machine you can experiment with. Okay, let's not go into much detail here. So here I already have like everything set up. So what I'm going to do is running the raw VM. Yeah. Oh, no, that's actually the wrong one, that one. So, the raw VM. What I'm going to do is I will run it on num course 1, and I will pick the demo image. Demo. And, well, it's a research prototype, so you see a lot of debugging stuff in the console, but any second now, there should be the actual image coming up. I hope. Yeah, there it is. So, the first thing you see is it's a very old image. So it's based on the MVC image from, what is it, Squeak 3.9. They stripped out the whole morphic part to be able to run on one of these Manycore systems, which is low on memory, which is low on performance, but is meant for experimenting with parallel execution. So what I have here is basically just a simple example. I do some output on the transcript down there, and I do some benchmarking, Fibonacci, as you might know it. And I just do it, it started, and as you can see now, well, I can't really do anything. It's one core, and then in the end we will get a result. The good part now is I can just stop that. Yeah. It takes a bit. And now started with 2 cores, and then it crashes. Great. Very good demo. Let's try it again. Usually it's stable, yeah? I don't know what's going on here, but so the same demo. We fork our block, and I can still play with the image, and at some point in time we should actually get the result. So, and that's basically it. So the virtual machine takes the process you're forking off here. So you take the block, you fork it, you create a process, and that's going to be scheduled on your second core if you choose to run with a number of cores that's greater than 1, and it's running parallel. Okay, so that's basically it. So there is not a lot of more magic going on. We didn't change a lot in the Smalltalk. The basic changes are additions to the process class. On the language side, we have like yield a fewer than certain number of cores for convenience, for algorithms where you know how many activities you have, and you want to make sure that you only actually give up the CPU if you really have to. You have things that makes it easier to make sure that you know on which core you can run, so we can figure out which is the current host core. I'm going to talk about a bit about the processor, and then you will see it's like a tile architecture. You have 8 times 8 cores, and you want to know exactly where you are. So that's useful for that. And basically the major change is in a squeak or Faro image you have, I think it's a processor global object, and you ask it for the active process. And that method is actually implemented as one variable that gets getting set by the virtual machine if there are scheduling activity. So the active process is really set to that variable. So you actually can only have one process. So we replace that by a primitive, and that primitive, this process, will basically just go down to the virtual machine and ask the current interpreter instance which process it's actually executing. And beside that, it's just a standard Smalltalk. So you have your do, your fork, you can send to processes, and those processes are getting scheduled in parallel. And you have your semaphore class, mutex class, and the rest is really the same. Okay, so the raw VM itself, it's basically a port of Squeak. It got rewritten in C++. If you look at the code, you will still see a lot of similarity with the Squeak code. We also reused the whole infrastructure in terms of primitives and plugins, so that part is fully compatible. We are not entirely up to date with the upstream versions. We update the stuff we need. For instance, I updated the file plugin to have good input-output, standard output handling, and so on. But beyond that, you will probably, if you do want to do fancy stuff, you will need to update that. We run on all kinds of platforms. We have a prototype running on the iPad. I don't have an iPad, so I can't show that off. But yeah, most importantly, the focus of the whole project was to run on the Talera machine, and there we can use, because of operating system limitations, up to 59 cores, and we can have 59 Smalltalk processes running at the same time, which is basically what the goal of the project was, to experiment with it. For anyone who is interested in the project itself, we have the typical infrastructure everyone would like to have. I set that up to have really, every time I check something into Git, have that building, have that running, have that tested. not only tested, well, we actually don't have that many tests, but most importantly for me is the automatic performance regression testing. So as you can see here, a spike. That's actually a time frame where we didn't have that yet. And one day I woke up, that was, of course, close to the deadline of a paper. I was running the benchmarks and figured out, why is it so damn slow? So it's like 6 times slower than usual. And then eventually I figured out, yeah, I introduced a bug there. So now we have that, and now we see immediately if I do something stupid and I can fix it. The code is at GitHub. You can clone it, fork it, use it as you like. Okay, so the general raw VM project, the code of the virtual machine is more or less frozen in the sense it works. Well, the demo effect you saw, there was yeah, the VM didn't start up. I don't know what's going on there, but that's perhaps because it's my experimental branch. It's a simple interpreter. It's really stable. David, Doug, and Sam have been using it. Max has been using it for, well, a couple of many years. Pablo, our student, used it for a year. And so when there were little bugs, we fixed it. But besides that, they didn't have problems. It worked. For the future, we would like to do interesting stuff, research, but we don't really have the manpower or concrete research project. So if anyone is interested in a parallel small talk to me, then we might be able to do something. Performance is, compared to Squeak, especially to the Coq virtual machine, not exactly exciting, but we can run on multiple cores, and if you have enough cores, then we can outperform even the Coq virtual machine. But you need a lot of them, so just to have that said. Okay, what was the original motivation to start another Squeak VM, another parallel Smalltalk? Well, at IBM Research, David and Sam, old Smalltalkers, were looking into the future of Manycore systems. So the big problem IBM has, their processor engineers tell them, okay guys, we can't make it any faster anymore. We can give you more cores every so often, every like 18 months or so, we can double the number of cores, but we can't make them inherently faster. So the projection is we will end up with thousands of cores on a single chip, not only in a rack or something. Today you can already buy big racks with 1,000 cores, but tomorrow you will have that on a single chip. We at the lab have it with 64 cores. People sell machines with 100 cores on a single chip already. And so that's the background, basically. And the question is, how can you use it? And one idea is to really harness the emerging effects you also see in nature. So you have here like the birds flying around, and they like have a very kind of regular behavior, and there is no global synchronization, it's just emerging. So the guys wanted to harness that. One problem with that is, well, in general, people assume parallel programming is hard because of the non-determinism. And the main problem is you have to synchronize to get rid of the non-determinism, and that kind of communication is expensive. So every interaction that's not only like on a local level between two entities that are close by, but it's global and has to involve more or all of the entities, that's expensive. You really have to get everyone in the same boat, and you have to wait for everyone and so on, and that takes a lot of computing power and reduces basically the overall throughput and performance of your system. So synchronization is a bottleneck, no matter what you do. Not only synchronization, in general, communication, every time you have to communicate, that's a bottleneck. So let's embrace that non-determinism we get if you don't have free-can communication, and let's try to figure out how to harness emerging behavior like we see it in biological systems. Yeah, so here you see the termite hill. It has like almost a very regular shape. If you don't believe in God, then, well, there is no global force that really drives these termites. And still they build a very, very intricate, complex building here that has not just a regular geometric shape, but but it actually is a termite hill with air conditioning and all the comfort these termites need. So it's a very complex thing, and they basically just have very infrequent local interactions, perhaps with pheromones or something. Yeah, and still they are capable to build these complex things, and there is not one architect like we have it in our world that has one big plan and plans out every single detail. Okay, yeah, let's do another demo. Ah, no. Particles. So that's a little demo Max Orhe implemented. The basic question is, what can we actually useful do if we don't over-synchronize, if we like think about the world in non-deterministic terms? And well, one of the classic problems students get taught in the introduction courses is like sorting. So let's sort those particles. So as you can see, they have different colors. That will be the main attribute we are sorting for. And they have also different sizes. I think that's not going to be terribly important in that demo. But the main idea is, okay, let's do it in a particle system and let them randomly collide and interact with each other. So what we do is, there should be somewhere a go. So what you can see now is basically there is no global interaction. There is just the local. Every particle is bumping into each other, and as you can see, relatively fast, you see emerging behavior in the sense that the colors actually like arrange into different corners. So here you have that kind of purple. Over here you have the greener stuff. You still see like that purple is kind of stuck there, and that one is bouncing back and forth and so on. But overall, if you step back and we would add more particles, then you see like it's relatively nicely ordered. So here we have a sorting that's completely non-deterministic, but gives nice results. Perhaps not precise, but good enough results for what you care about. So, and depending on the application, that's really you want performance, and you might be able to give up accuracy and precision like you do with, for instance, floating point numbers. Okay, let's call that. Let's go back to that one. Normally I demo that stuff on the machine I have back in Brussels with 8 cores, a lot of memory, a lot of power, so that takes here a while. I don't know what's going on. Here we go. Okay. That one. So what you can see now is basically a simulation of birds flying around. So that's a Boyd simulation. There's a neat paper describing a mathematical formula to approximate the behavior of birds in a flock. And as you can see here, they basically try to stay close to each other. They move more or less randomly about, but no single bird ever completely leaves the flock and disappears. So they bounce off from the sides, but beyond that, they basically move in their own direction and try to orient each other to their neighbors. And yeah, so it's still like a consistent system. Nobody leaves the flock. And again, there is no global synchronization, and every process, basically every bird, is supposed to run on its own processor, which I can't show here with my local machine. And that demo was implemented in the Sly language. And the basic idea behind Sly is that you actually don't really work with objects. Instead, you work with so-called ensembles. Because the idea is that you don't usually want to refer to a single object, especially in a parallel case, where you want to work with big data, with data sets that go beyond single, small arrays and so on. You really want to work with collections, and you want to have that notion as a first-class notion in your language. So they started to call it ensembles, and the main idea is that if you send a message to an ensemble, that actually also gets sent to all the members of the ensemble, all the items in that collection. And most important for the language aspect is that you have the notion of adverbs and gerunds. So from the English language, you basically use it as modifiers for operands. You have the adverb individually, serially, randomly, and others. Basically, Sam made a list from the dictionary and tried to pick out all the useful ones, and actually he figured really all of them are useful in different ways to describe how to actually apply an operator. So as you can imagine, serially will really just make sure that the operator the message you're trying to send to the ensemble is serially applied to all members of the ensemble. Randomly will just pick out random elements, exactly n elements from the ensemble, and will apply the message to that. And individually will take every single element out of the ensemble and apply the result, the operation individually. Okay, the gerunds are basically the reduction semantics, or to say that the other way around, it's a way how to treat the result of the operation. And well, as you can imagine, ensembling is the standard behavior. Every time you send a message to an ensemble, it will be applied to all the elements, and what you get back is a new ensemble with the results of that message. Other interesting ones I'm going to show here are averaging. So you get the average over all results, and selecting with a predicate that will give you all the elements of the ensemble that actually fulfill that predicate. So it's a small little extension to Smalltalk by annotating your message sends that works in a kind of MapReduce style and works on these ensembles. Okay, so to give an example, so based on the flock simulation I showed, the Boyd simulation with birds moving around, one of the most important things is you want to, as a bird, you look around and you try to find where's the center of the flock to not get too lost and to stay close. So what you do is, you're the bird, you know your flock you belong to, and in that flock are all the other birds. And what you do is basically, you want to know all the positions, but basically you want to know the middle, so you say averaging on the positions. And here a little, well, more optimization, more demo, because every bird is conceptually executing on its own core. We want not to do too many additional parallelism because that has scheduling overhead. So we say, okay, let's do that serially. Let's look at all the Boyds in my flock and get the average, the central position. Similarly, I also want to coordinate with my neighbors, so the birds that are close to me. And to figure out who the neighbors are, we again go to the Boyds and basically do the selecting with a method that's implemented on a Boyd is near, and well, it's near to myself. So the result will be a collection of Boyds, an ensemble of Boyds that is close to me, whatever is near precisely is. And what I then do is, based on these neighbors, I can, so self neighbors uses the compute neighbors, and then I can actually match my own velocity based on these neighbors' velocity. Again, I average that and apply that factor here. And so that's basically the math behind that simulation, using Sly as a language, as a MapReduce kind of language, to do that computation. So the general idea is every bird executes in parallel, and these operations, if it's not especially annotated with serially, can be executed in parallel. And as a programmer, well, that model is still making sure that if that returns here, then actually all the parallel activities we have spawned, especially here, are completed. So you have really like inside of your bird, you still have like a parallel programming model that uses a sequential programming model that uses the parallelism available to do this stuff. But as a programmer, it's more or less a common way. You don't have to really do explicit forks and joins. That's implicitly done by that language extension. For a brief overview, Pablo wrote a nice write-up. You will find it here at the URL. Okay, so that's a very experimental language, and you might wonder what to use it for. Well, the IBM guys, they have these big machines, and they have customers with a lot of data. And one of the big problems they have is, okay, we have like big data sets. That's like data about customers, that's data about customer behavior, and they want to make predictions, they want to make business decisions. And what they have for that is these kind of cubes. It's basically spreadsheets on steroids, multi-dimensional spreadsheets. They call it online analytic processing, roll-up. And what they do is they try to query these things. Some of these dimensions might be computed, need to be recomputed if you insert new data. You want to do all kind of complex queries that combines different dimensions of these cubes. And well, that's very computational intensive. But a very important property is that data is usually like either human entered or like generated, measured. It's not 100% precise. And you typically don't need absolute precision. What you need is to be able to answer a lot of questions fast to get a good understanding what's going on in your business. So we can actually try to use these properties to, well, we don't need absolute precision. What we need is absolute performance. So we need to answer many queries fast. So we can take race conditions and live with them and try to have the overall result reasonably correct. So that's one of the real-life applications. Another one is gesture recognition. That's actually something we do in Brussels. There's a PhD student working on using declarative languages to express gestures. So if I move my arm in a circle, well, if I would be a machine, that would be very precise, and it would always be the same circle. But if you imagine you stand in front of, I don't know, Microsoft Kinect or something, play a game, the circle is not always a circle. You still want to recognize it. So the input data for that is also inaccurate. And you have to have some kind of fuzzy matching rules. And for that kind of stuff, actually our, like, as we call it, the race and repair programming model, where you really use all the parallelism you get, and only if you really have to afterwards, you fix up results if you need to, works pretty good. So that's something we are looking into, and well, IBM is more interested in the business stuff. Okay, that's more or less what Sly and the general direction of that research project is about. What I'm going to talk now about is the actual raw VM implementation. So that all started with David Unger and Sam Adams having access to a Talara prototype. That's a 64-core machine that looks a bit like that. So that's just 9 cores. The most important part is those are really in a tile architecture. And every tile is connected to its 4 neighbors. So to every site, basically. And the important part is that the memory connections are only somewhere at the borders of those chips. and there are like 2 or 4, depending on the model, connections really to the main memory. So it's kind of, if you somewhere in the middle or at another corner need access to memory that's well managed by the other edge, then you have to hop through the whole ship and then go to the memory controller and then wait for the main memory to respond, and only then you actually get the data. So that's very costly. So one of the main design decisions was, okay, let's to try to utilize the extra hardware they actually offer. So I depict like here 3 channels, and one of them is for main memory access, one of them is for intercore communication, and one is for cache coherency and that kind of stuff. And so if you implement that virtual machine, we want to communicate between the interpreter instances, and let's do that with message passing, because here you see a couple of numbers that's like at least 1 order of magnitude faster than going via the main memory, which is a typical way of implementing virtual machines. So if you imagine how a VM runs on that, then basically every core hosts its own interpreter instance. They are part of the same Smalltalk, overall Smalltalk image execution. So it's a single system image. You still, as a programmer, you still have the illusion and the experience of a shared memory system, but they basically run independently on the different cores. So what we do then is basically for VM operations like garbage collection and save points, we really use the explicit communication facilities. We send messages between the interpreter instances to do like initializing garbage collection. You have to reach a save point, you signal that via message passing instead of setting a flag somewhere. So if you look into how we actually build the memory subsystem, the organization of the object heap, the object memory, well, one important point is very early on they made the decision they use an object table, which is kind of an outdated concept. No major virtual machine uses an object table anymore for the standard object heap. The main idea here was, okay, we have these different cores. We know that there are different memory access properties for the different memory. So we would like to move objects around if you need to make it fast. And with an object table, that's very simple. Because of that additional indirection, you can just grab the memory of that object, move it around, fix up the object table, and then you're basically done. And you don't have to query and traverse your whole heap to fix up all the pointers. Yeah. So we have an object table at the moment. The garbage collection is a moving garbage collection that utilizes also that object table, and at the moment also stops the world. I'm going to talk about later what that means. Yeah, and most importantly, to get allocation fast. So Andres was talking about use objects, allocate a lot. So if you really do object-oriented programming, you need a fast allocator. So the fastest thing we can imagine is a pointer bumping allocator. So you basically just add the size of the object to a number, and then that's basically everything you have to do for allocating objects. So what we do is basically every interpreter instance at startup, we have, as you may have seen that I give the parameter how many cores I'm using. So that's static. That's something also to simplify the virtual machine. We actually don't allow at the runtime to change the numbers of cores we are using. That's static. So we also divide up the heap statically. Yeah?
Quick question. Does the Tyler chip come with some sort of SDK that provides you with some functionality, or do we have to write all the mechanism for inter-core control yourself?
Well, they offer, actually they offered, they don't do that anymore. They offered an SDK where you really have like the standard library functions, send a message over there to that core, and you can do that. So that infrastructure is there. You don't have to do that on a low level. Okay. Yeah, so we have a static heap layout. Basically every interpreter instance works on its own part of the heap. Reading and writing to objects in different parts of the heap is perfectly possible, so it's still shared memory, as I said, for the programmer. But allocation and moving of objects is problematic. So what we have to do is basically, to make it simple for us, we assume that it's not a common operation, that you have to move an object from another part of the heap around, or moving objects in general, or allocating objects in another part of the heap. Then you have to send all the other interpreter instances to a safe point, wait for them, that they stop, don't mess up your heap while you're trying to do that critical operation, and then you only afterwards you can continue. Another important aspect of that virtual machine is the introduction of a so-called read-mostly heap. So as I said, the system they were using was more or less a prototype. So by the time today, things changed already. So cache coherency is a very important property you have to have in a shared memory environment with multiple processors. You want to see the same things in the heap. You don't want to see inconsistencies. In Java, you have a memory model to know exactly, precisely when things get visible. And in the hardware, you have cache coherency to make sure that your write to the main memory actually is visible in all the other cores, and that you flush caches, that you make sure nobody is working on the old data anymore. But that's very expensive, especially if you have 64 cores. That was the original stuff they were doing was so slow that was not really an option. And it's not clear how engineers can be smart enough to do that in a 1,000 core or 10,000 core machine, that you still get that kind of cache coherency. So David was looking into a way how to actually, build a virtual machine with the assumption that we don't have cheap cache coherency. So what he came up with is to divide the heap in two zones. So the read-write heap is a normal heap. You can do everything, reading, writing objects there. And in the read-mostly heap, you basically put only the objects you actually will, most likely not change. Methods, classes, general data objects that are seldomly touched after initialization will go there. And what then can be done is you basically can usually tell that kind of hardware that part is actually incoherent, and the different parts, the different interpreted instances are allowed to cache it without having to worry about anything. So then you avoid the overhead of actually managing cache coherency. You have to do it yourself, but here we just assume it's seldomly happening that we actually write to these objects. So we get a decent speed up by allowing these kind of inconsistencies in the VM. Then we have, of course, to have the additional checks to get it right. But yeah, so that was a solution they proposed, and that gives decent speed ups on that kind of hardware, especially, it will most likely be necessary for really big 1,000 core chips where you really have different, where you have a lot of problems with cache coherency in the first place. Yeah? 5 minutes. Okay, well then let's make it quick. So stop the world, I said, if you imagine 64 cores, you have to synchronize them all to get to a certain save point where you know what every thread is doing, and that takes time to arrive at that save point, and then only then you can do garbage collection, object movement, and so on. That's a problem. So if you imagine that situation, you really stop the world. You have 64 parallel activities running at the same time, and you have to wait to synchronize them all. So that's really an overhead. So what we did, and actually designed by other people, there's a nice paper from 2005 where they designed a non-stop the world, a pauseless garbage collection. We have a prototype of that. That's a very nice algorithm. It's relatively easy to implement. So those two master students took a month to get that prototype running. It still crashes after 2 iterations of the garbage collector, but the basic principles are there. And now, the engineering is kind of missing. The drawback is there is kind of a constant overhead because you do like on every read you check and try to self-heal the heap, but you don't have to wait anymore for any of the other activities. You have a garbage collection in the background which does all the important garbage collection tasks like marking and sweeping over your heap, but you don't have to stop every other application thread anymore. Yeah, there are a couple of more prototypes like getting rid of the object table because that's a lot of performance overhead, trying to get better performance by using operating system processes instead of threads on top of OS X and other standard Unix operating systems, because that actually brings a lot of overhead, and if you use an OS process, that's something we notice, the compiler can do a lot better job than with if you have to use thread locals. Some people might know that if they implement a reentrant interpreter, that's typically slower than if you implement one that relies on global state. We have a prototype for scheduling per interpreter that's meant to facilitate very fine-grained parallelism and to really improve the overall scheduling behavior. Unfortunately, that one is stock slow, but yeah. If you have these kind of problems and if you try to experiment with a raw VM, we have benchmarks where it actually gives speed up, but in general it slows down. So you might want to look at that. That's all online, that's all open source and available. Okay, to conclude the talk, well, so Sly is a MapReduce-like language that gives you gerunds and adverbs to define the semantics of your operators, and you work on collections, on so-called ensembles. So instead of really taking a single object as the thing you operate most with, you really think about ensembles in terms of collections of objects. The raw VM, it's a research artifact. It's not entirely, well, up to speed, but it's useful for experiments, especially if you're interested in parallel smalltalk. Go grab it, experiment with it. You will see all the words, but you can still experiment with parallel smalltalk. Okay, so if you want to find it, here are the URLs. Go look at it. There are a couple of introductory material up there where you can read up on Sly and how to use the raw VM. And yeah, if there are any questions, I'm happy to answer them now. Thank you. Yeah.
Let's say that in the previous slide the raw VM shows weak scalability.
Weak scalability is a term they use in the supercomputing universe. That means if you can increase your problem size, then you get scalability. The problem usually is if you have a fixed size problem and you want to bring that up to speed on more cores, then you have to reduce the sequential parts of your actual algorithm and your problem. But if you can increase the data set, then you often can get what they call weak scalability and still get, like, for every core you add, the linear speed up you want. So the VM is prepared for that, but we can't do magic with the algorithms.
Okay, so thank you very much.
Thank you.